So part of this work is done in collaboration with my former PhD advisors, Arnold and Patrick Popescu-Pampu. And before I tell you the structure, let me tell you what objects we are going to consider. So we look at real algebraic domains. So these are closed topological subsurfaces in the real affine plane. And they are bounded by disjoint, finitely many smooth connected components of real algebraic plane curves. And you can see already some examples. Here we have a compact algebraic domain, connected. You can also have non-compact and connected. We can see an example here of non-connected, non-compact. So quite interesting shapes one can find. Just to be sure that, like, to have a concrete example here of an algebraic domain, if we have this real curve in red, real algebraic curve given by this equation, and it has two connected components, an oval and a component homeomorphic to a line, and consider another one here by this equation in blue. Again, it has an oval and a component homeomorphic to a line. And then the ring surface here that you can see in gray is an example, by definition, of an algebraic domain, real algebraic domain. We only consider real, so I will not mention this. And you see, we just ignore this line. So this shows this example that real algebraic domains are more general than just semi-algebraic sets. It's a more general notion than that. So what is our goal with these objects? We want to study their non-convexity, to measure this non-convexity. But this turns out to be a difficult task, so we will just measure this non-convexity in a certain direction of projection. And for us, this will be the vertical projection. And you might wonder how to do this. Well, I'll tell you very briefly, and then I'll go into more technical explanations in a few slides. But the idea is that by collapsing the domain into a graph, we will be able to use combinatorics to measure the non-convexity. So essentially, for instance, if you have this compact algebraic domain, if we take each maximal vertical segment inside it, and we contract it into a point, we get a planar graph, and in this case, a finite graph. It's actually a tree for this example. So now once we have these objects that I will explain more in detail soon, we can rephrase the problem in terms of trees or graphs, depending on what domains we have. And now the question would be to classify all possible such topological types of such graphs. So roughly speaking, if you are given such a graph with some properties that I will mention, can we construct a real algebraic domain that realizes this graph via this collapsing procedure? And that's the whole thematic of this talk. So also you can see this talk as an invitation to start studying Poincaré-Reeb graphs, because I will show you that they're useful in several directions. So the talk will be divided in 3 parts. First part, I will focus on algebraic domains that are bounded just by a topological circle near a strict local minimum. I'll tell you more precisely soon. So more than half of this of the talk will be focusing on this. Whereas then we will go, I will generalize this for real algebraic domains, as I mentioned, as I showed you before, what objects we consider. But in between, I will also present to you the most general context that we could find in which the construction, this collapsing procedure, can be applied such that the graph will still be embedded in the plane and will have finitely many vertices. Because one might want to use this collapsing procedure also in other contexts with no differentiability assumptions at all. And for just the new part, this part with real algebraic domains, you can find it in this preprint on the archive that we uploaded in July. And this is joint work, as I was saying, with Arnaud Baudin and Patrick Popescu-Pampu, whereas the part with the strict local minima consists of these 3 papers here. So let's start with the first part. This is this context, I will say it now, with strict local minima. So if we consider bivariate polynomial functions, and with the property that they vanish at the origin, and they have a strict local minimum at this point, we will look now at the level curves near the origin, f equals epsilon, for a sufficiently small epsilon. So this will be the boundary of the real algebraic domain that we consider in this first part. So for the simplest example, this circle, x squared plus y squared. So these are smooth, these fibers are smooth Jordan curves, okay? And we want to study the shapes of such curves. Of course, here there's nothing new for the circle part, but let's see. If the strict local minimum is Morse critical point, so if it's non-degenerate, then the small enough levels that approach the origin become boundaries of convex topological curves, disks, sorry, convex disks. And we call these just convex curves. You can see that curves further from the origin might be non-convex, but when we approach, they are boundaries of convex disks. And you might wonder whether this is always true. So does it always happen that near a strict local minimum, the level curves of such polynomial functions will be convex? So this is the starting point of this work. This question that Emmanuel Giroux asked to Patrick Popescu-Pampu in 2004, whether the small enough level curves of this f function near strict local minima are always boundaries of convex disks. The answer to this question is negative, and this is due to a counterexample given by Michel Coste. This polynomial here has a non-Morse strict local minimum at the origin, so a degenerate minimum, and its level curves will never become convex when they approach the origin here. These are some of the levels. So turns out that there are interesting shapes that one can find, and this is the research problem I want to talk about today, about understanding these non-convexity phenomena. That's my goal as a general goal. And as a sub-problem, I constructed and characterized a large class of non-Morse strict local minima that are far from being convex. So here you can see this is this example by Michel Coste, and already in the middle and the right picture there are some more complicated shapes. So you see that you arrive to this question somehow of one can ask how to measure this non-convexity, how to say which is more non-convex. So the question would be now, with what combinatorial object one could encode the shape by measuring the non-convexity of a smooth and compact connected component of an algebraic curve in the real plane. So there are several, one could think maybe of different objects, but the object that I introduced, doesn't work, is the Poincaré-Reeb graph. In this case, it will be a tree, I will tell you. So, just a second, I jumped one slide. So, the Poincaré-Reeb graph that is associated to our curve and to a projection direction. In our case, I said we focus on the vertical projection. Let me tell you how to define this graph. If you have here the curve and the disk bounded by this curve, consider this projection, and then if you take a point x0 on the real axis, look at its pre-image inside the disk via this projection. So in this case, it is a union of this green vertical segment and the pink one. So what we do now, we will pass to the quotient. So essentially, we will contract each such vertical segment into a point. And if we do this, you see that the green vertical segment here becomes this green point on the graph. And the pink one becomes the pink point. So in other words, if you do this for all the points, you end up contracting the whole disk into a graph. And the vertices of the graph are points of vertical tangency on the curve. So you have.
How are they connected? I didn't understand how the connection of these two vertices or edges here appear. Can you explain?
Excuse me?
The edges between vertices.
Yes, the edges will be contractions of bands between two consecutive vertical points of tangency, and those bands are formed by vertical segments that you contract. And then the vertices make this delimit these edges. And the name, the Poincaré-Reeb graph, is due to, so I chose this name because this construction is inspired from a classical one due to Poincaré, who was using this as a tool in Morse theory, and it was rediscovered later by Reeb in higher dimensions. But in this setting, actually, the Poincaré-Reeb graph is a transversal tree. So it is a plane tree, it's embedded in the plane, and these open edges are transverse to the foliation induced by the vertical projection, by the fibers of the vertical projection. And moreover, because the function x descends to this quotient, we have a total preorder endowing the vertices of the graph. Preorder, I'm saying preorder just because there can happen that the curve has bitangencies, vertical bitangencies. So this is important to keep in mind throughout the talk, that we have a preorder on these vertices. We don't care about the precise coordinate of the points, but of their relative positions. But remember, we were studying these level curves in families, so we look at level curves that are near the origin, smaller and smaller level curves, f equals epsilon, when epsilon tends to 0. So if you associate a tree to such to each level, you will get smaller and smaller trees, and starting with a certain epsilon, these trees will become equivalent. So we say that the shape stabilizes. So near the origin, the shape of the levels will be stabilized. And moreover, these trees, these asymptotic trees, are rooted because there is the image of the origin. You can consider it a root. And the total preorder on the vertices that I was talking before becomes strictly monotone when you look on geodesics that start from the root towards the leaves. So in particular, this configuration is impossible asymptotically. Just need to see if I have a better. So it is, you cannot have turning back like this for your curves near a strict local minimum. You don't have spiraling phenomena. Just I see that the thing doesn't work. So maybe this works. Yeah. Okay. So these spiraling phenomena don't appear locally. You don't have such thing. Okay, then I need both. So now that we have this formulation in terms of trees, we can restate the problem, the non-convexity one, in terms of trees. So we want to characterize all topological types of Poincaré-Reeb, of asymptotic Poincaré-Reeb trees. And in particular, now we can think about the construction problem as follows. If you are given a transversal tree, so I was saying that the edges were transverse to the vertical foliation. If you're given a transversal tree, can you construct a polynomial with a non-more strict local minimum at the origin that realizes this tree via this collapsing procedure of the Poincaré-Reeb construction? This is the question that I am going to consider, and to this question I have a positive and a constructive answer. So this is the main theorem in the first part of the talk, but just I want to mention that before that I need to introduce some more, in order to understand this theorem more technically, we need some more notions, combinatorial objects that appear, and we also have to pass by the univariate scenario first. So we will see a construction of prescribed shapes of polynomials in one variable that I will use then to prove the main realization theorem, that is the following. So given a separable transversal tree, we can construct the equation of a bivariate polynomial with strict local minimum at the origin, realizing this tree. These other adjectives are technical. For now, important is that for a large class of transversal trees, that is the separable ones, I can give this construction effectively. Good. So for the first part, this is the main result. What tools do we need in order to make such a construction? So the first tool is the real polar curve. So this, by definition, is the set of points in the real plane where the partial derivative of f with respect to y vanishes. So geometrically, it's the set of points in the plane where the level curves have vertical tangency points. So you see that when we consider these level curves in families, then each such level has a point, and the points move along the branches of this red curve. And this is the real polar curve in this example that I was mentioning from Michel Coste. So you might think, why would the polar curve play such an important role? This is because here in the right picture, you notice that you have the vertices of the Poincaré-Reeb graph are actually images of points of intersection between the polar curve and the levels. So by understanding or controlling the polar curve, one could control the shape, and thus one could control the graph. The second tool is a choice of a generic projection. So we need to choose our projection, and this has to avoid vertical inflections, and it needs to avoid vertical bitangencies. You already could guess that we want to avoid vertical bitangencies because this would stop us from having a total order on the vertices. You have vertices on the same vertical line. And here we would like to not have such situations of vertices of valency 2. So in this genericity, under this genericity hypothesis, then we can show that the trees have their vertices endowed with a total order. So in this case, we can order completely the total ordering. We have a total ordering on the vertices, and moreover, the trees become complete and binary. So each vertex has precisely 2 children, each internal vertex of the tree. And this total order actually helps us distinguish between these 2 trees. These 2 trees are not equivalent for us, because if we want to go from one to the other, we would need to have this bitangency phenomenon, which is prohibited. So we saw what happens asymptotically, now generic and asymptotically. Now we need also another tool that plays a very important role in the proofs. This is the discriminant locus of a certain projection map. So you see here we have this level. Say f equals epsilon would be a level in the x, so y plane. And then if you look at the graph that is the surface of equation z equals f of xy. Here you have, let's say, a part of it. When you project this graph on the vertical plane x of z, you see that a special area appears here, and this is in red. This is called usually the apparent contour of this projection. And the image of this apparent contour under this projection will be the curve delta here. Then this is the discriminant locus of our projection. In more algebraic terms, if we have this phi that sends xy to the pair x f of xy, then the polar curve from before is the critical locus of this projection, and the discriminant locus will be the image of the polar curve via the map phi. And this genericity hypothesis I mentioned before can be also explained in terms of the polar curve and the discriminant curve and the interplay between these two. So remember, we wanted to avoid vertical inflections on the levels, and this is equivalent to the fact that the polar curve is reduced. Here, okay, we just look at the positive x for now. Starting from now, we just focus on the sides of the semi-plane x positive. And the second genericity hypothesis was the fact that we want to avoid vertical bitangencies. This would be equivalent to the fact that this map phi sends the curve, the polar curve gamma, homeomorphically onto the discriminant curve. So we don't want two branches of the polar curve to be sent on the same branch of the discriminant. But under this genericity hypothesis, now I need to introduce one more combinatorial object that will help me make computations in my construction, and this is the positive snake, positive asymptotic snake. So I was saying that from now, for a while, we just focus on x positive, so this semi-plane. So we look at the part where, of the level curve where x is positive, here near the origin. And if we consider the points of intersection between the polar curve and the level, these red points, then you, under this genericity hypothesis, you can endow these points with two total orders, as you can see from the colors. So the one order is just by following, if you want, following the level. So this would be 1, 2, 3, 4, 5. And the second one is the one induced by the vertical foliation of the plane. So this is the green one. Just by convention, starts from right to left, doesn't matter now. And by comparing these two total orders that endow the same set of objects, in our case, these are the red points, you get a permutation. And what is even nice is that always in this case, you get an up-down permutation, or you can call them a snake. And you see here, because you get the first one arrives in the first position, the second one here arrives in the fifth position, so 2 goes into 5, and so on. So this is an up and down permutation. Why I called it a snake? This is because I was inspired from Vladimir Arnold, who used this in the univariate setting. He associated snakes to graphs of univariate Morse polynomials. So a Morse polynomial has all its critical points real and distinct, and all its critical values distinct. Here is a picture of such a graph of a Morse polynomial, and Arnold did a similar thing. I mean, that's what I was inspired from. He numerotated the critical points, and in a separate way numerotates the critical values, then compares these two total orders, and he also obtains a permutation that is zigzag, an up and down, snakes. Okay, so we are approaching slowly to this univariate scenario that will help us make the construction with this thing. Because, okay, using Arnold snakes, we will be able to reduce the problem to univariate case. So if you had, remember we have here the snake in two variables in the horizontal plane of the level. This say it's sigma. And now if you consider the graph of f, you cut it with the vertical plane x equals x0 for an x0 small enough positive, then you see that this graph here is actually the graph of the univariate polynomial that only depends on y. And for a sufficiently small x0 here, actually this is a Morse polynomial, f x0y. And even what is very interesting is that the two shapes are the same. So you can say that the two permutations, so sigma equals tau. This means that if we could construct univariate shapes as we want, then those will be reflected in the bivariate levels, so or the levels of the bivariate polynomials. The idea, just a brief idea of the proof, is that the interplay between the polar curve and the discriminant curve gives us this equality. Just to know what. Okay. So maybe I don't go into detail, but if you look at how this curve, I was telling you there is a map that sends the polar curve into the on the discriminant curve. If you look at how this is sent on the green curve, that map from before, you can compute the permutations and see that they are actually equal to the permutation obtained by this comparing the blue and the green curve, the polar and the discriminant curve. Okay, so I just want to recall, we want to construct, so if you give me a transversal tree, I want to construct a bivariate polynomial that has that shape near the origin. And I recall that for separable transversal trees, I gave a positive answer. So then what does it mean to be separable? In order to explain this definition, I need to, I need to tell you that, first of all, there is a bijection between transversal trees and permutations, because we are talking about trees, but separability is a combinatorial property that is in terms of permutations. But we are lucky because transversal trees, so those that should be realized, are in bijection with snakes. So again, if you numerotate how to show this, if you give me a tree, I can get a snake. This is a different procedure than before, I mean, a different tree. And then the other way around, maybe I skip the details, but you can also, from a permutation, you can also get to a tree. And then just rotate it so that it's the tree to the right of the origin, like we want. I can explain here, this is an algorithm. So it's a short, simple thing. If you have a permutation, actually we need this further. Once you have a permutation, you can encode it geometrically with placing dots in a square. So if you have 5 goes into 2, then you place a dot into the square 5, 2. And so you obtain a geometric encoding of permutations. So when you want to find the transversal tree associated to such a snake, just place the dots according to the permutation, then apply the following algorithm, which is due to Richard Stanley. He was the one who used this, and find what does it say? To find the highest vertex in the square, and then divide the blocks the block into 2 subblocks, so left of that higher one and right. And then to process recursively, to do the same, you find the highest vertex and you continue decomposing into blocks. And at the end, you get this graph. So just the whole thing to remember here is that to transversal trees, one can associate bijectively snakes. And now what is, oh, this doesn't work. Okay. And now I want to explain what is a separable tree, separable transversal tree. For this, I will tell you what is a separable permutation, and then we should understand what that is. So a separable permutation, once we have this geometric encoding of permutations, I can explain better. I can decompose, so separable permutations can be decomposed into 4 blocks, and such that 2 of them are empty. And at each step, you can do the same with the other blocks up until you end up having just blocks of size 1. So in this case, you see this was a possibility, and it's not, this decomposition is not unique due to the associativity. The idea is that you get a binary decomposition tree out of this. If it's a separable permutation, you are able to obtain a binary decomposition tree. And of course, not all permutations are separable. If you try to take this permutation, you start decomposing into 4 blocks. This works the first step. But the second step, you won't be able to do this. These permutations were recently completely characterized by Etienne Gis in his book, A Singular Mathematical Promenade, in terms of graphs of polynomials. Okay. So they are they are well understood. Now, finally, what is a separable tree? Separable transversal tree. It is a tree to whom we can associate a separable permutation, because we said there is a bijection between trees and permutations, and now if the permutation is separable, then this is the condition that we are working with. Good. Now we understood what classes of trees I can construct, and how do we? I was telling you that we can reduce the problem to the univariate case at some point, and already you remember that we were doing this cutting with the surface with the plane. So, okay. So given the shape we want to construct, let's consider the same shape as let's try to construct it as a graph of a univariate polynomial. So now the question becomes, given a separable snake, like here, can we construct a Morse univariate polynomial that realizes this graph that realizes this permutation as with its graph? The answer is yes, and let me show you how to do it on a particular example to understand better. So if you have here this snake that is separable, you take one of its decompositions into blocks, so you obtain a binary decomposition tree. And now we will look, this is, we focus on this tree. This tree will allow us to construct polynomials in one variable if we decorate it in a nice way, with the decorating procedure that I will explain now. So it gives you quite a lot of freedom, this decorating procedure. You have to add monomials in the vertices and coefficients on the edges. And then you will, you need to consider that this is an embedded tree, the plane. You need to have a strictly increasing order on the exponents and also on the left edge and right edge. Maybe I'll skip this detail, but there are just these constraints. And then you can read univariate polynomials starting from the root of the tree towards the leaves. So if you want to read A3 of x, you have, you see that it's x times 0 plus x squared times 1 plus x cubed times 1. So this gives you x squared plus x squared. So from this tree, you can get to a set of univariate polynomials. And actually, you can also do the other way around. If you have a finite set of polynomials in one variable, you can associate to such a set a tree that encodes the contact between the polynomials. So you see that A4 and A5, they are the same up until the power 1 of x. So you have A4 and A5, they start splitting with x squared. So it encodes how they are the contact, and this can be really this can be seen by the graphs. When you plot, if you take a computer algebra system and plot these graphs, you will actually see this contact. And now we are ready to see the construction in the univariate setting. So for univariate Morse polynomials. Now, remember, we are given a separable snake, okay? And let's define a polynomial, Q. It's in a polynomial in Y, but with coefficients polynomials in X. Okay, this might make you think of what we were seeing also this morning from Chris' talk, but just it's not direct relation. Just that the coefficients will be polynomials in X, and what we do. So essentially, we take the product. We have all these AIs that we constructed starting. Okay, no, we have the snake. We decompose the snake as I was showing to you, and we get these AI of X polynomials in one variable. We plug those into this product, and then we take the integral. And this polynomial, Q of Y, for a sufficiently small x positive, is a Morse polynomial, and its Arnold snake is the given one, sigma. So its shape is the one given by the permutation sigma we started with. So starting with this permutation, take this recipe, take this polynomial. If you plug in as x small enough, you will get a univariate polynomial that has the desired shape. Okay. For the bivariate question, now add in front of the previous construction an x squared, and look at this polynomial as a polynomial in two variables, x and y. Then this polynomial has a local minimum, and the right side of the origin has the desired shape encoded by sigma.
Sorry, is it easy to see that this is not negative?
That has a strict local minimum? Yes. It's really required the proof I used needs Newton polygons. There's a criterion in terms of Newton polygon. So you assume that it's not. Start with contradiction, by contradiction, and you then get the contradiction by using a Newton criterion polygon. Because in this family of polynomials, and I will tell you this maybe afterwards, has just one compact edge. So that's the key point. It's not obvious. Not too obvious, I think. Thank you. Okay. So. What you were saying, indeed, the family has a strict local minimum, and to the right-hand side of the origin is what we want. But remember, at some point I said, let's just focus on what happens for x positive. So I didn't say anything about what happens to the left-hand side of the origin, and I didn't control this up until now. So you might wonder, okay, we constructed the desired shape to the right. What happens with the left-hand shape? What can we say about that? And for that, I need just some observations to make. The polynomials AI of x that were constructed with the contact tree, they are actually their graphs are actually the polar curve of the polynomial f. So actually, what we do, we construct the polar curve by constructing those AI of x. So in this family, the polar curve has all smooth, because they are graphs of univariate polynomial, smooth, real, distinct branches, like in this setting. And we controlled what happened to the right, but this influences, via this real polar curve, what happens to the left-hand side. Because when we decorated the graph, remember we had a decoration, we just chose these monomials as we wanted, as long as the exponents are strictly increasing on the geodesics towards the leaves. And I didn't say anything about what parity one could use here. You could just choose x squared and then, okay, so it will still work. And now comes the interesting part. If you consider, say this is the horizontal axis, and if you have a polynomial that crosses this horizontal axis at the origin, the key point here is that the polynomial will cross the horizontal axis if and only if its valuation, so the exponent of its smallest monomial, of the smallest degree monomial, is odd. So in this case, you see that this crosses the axis, but for x squared plus x4, it does not, it just bounces back. And in other words, one can say, or one can also deduce, that two polynomials, when they meet at a common zero, they exchange their positions. So here, this one was above the blue one, whereas when they go out of the origin, the blue comes above the red. So they exchange their positions if and only if the valuation of the difference of the two polynomials is odd, like here. Otherwise, they keep their position. This is a picture taken from Etienne Gissi's book, where he studies this very in detail. But these trees, these contact trees, in our case, this matters because if this is exactly what happens for the polar curve. If here we placed an odd exponent, then when it crosses the origin, the polar curve will interchange the two trees. So you see that this tree that has as a set from 1 to 5, it was down, and now it becomes up. And this will influence the shape to the right, to the left of the origin of our level. So I have an algorithm, that's the flip-flop algorithm, that tells you which pairs you can match with a given shape once in this family of polynomials. Okay, maybe there are other shapes, but with my family, just this, in this example, for instance, just these 4 you can have to the left. Okay, now, so this was the first part where the algebraic domains were bounded by a real Milnor fiber. So they were just topological disks near the origin, bounded by this connected component of a real algebraic plane curve. And in this setting, I had this effective construction. And now, I mean, don't worry, the second and third part are not as long as the first. Otherwise, time would not be enough. Before that, so starting with now, this is the new preprint together with Arnaud Baudin and Patrick Popescu-Pampu, starting with part 2 and 3. And we wanted to show that this construction, we thought that this Poincaré-Reeb graph construction could be used in also more general settings for more, like without any differentiability assumptions, and for instance, for piecewise smooth, so for domains bounded by piecewise smooth functions or other less regular objects. And remember that we were using this collapsing procedure when, and maybe now your question comes more clear. I don't know if I had this figure before. This is a band in between two critical points, and it becomes an edge once you contract it. So when we make this contracting procedure, we end up with a graph embedded in the plane. So after all, we end, if you look at the whole, the result, actually it is, we obtain a surface that is homeomorphic to a plane. So, but however, we cannot canonically say which plane this is. We just know that it is, again, a real plane. So this motivated us to give a general definition of where one could apply these graphs. So we say that a pair, P pi, is called, so a pair is called a vertical plane if P is a topological space homeomorphic to R2, and we have pi a locally trivial topological fibration. So just to keep in mind, the canonical way is R2 with X as we had before. So this is just a generalization. And we need one more in order to define which domains are the most general we could find, where the construction still yields a graph that is finite and planar. I need to also introduce the topological critical sets. So these are just, so if you look at the curve in the plane, the topological critical points are those where this pi restricted to the curve is not a local homeomorphism. So these two are topological critical points, and this is not. So an inflection point where the curve crosses the tangent won't be considered for us topological critical point from now on. And the most general setting we found is, so for which we could construct Poincaré-Reeb graphs, is what we call domain of finite type in a vertical plane. So by definition, this is a closed subset homeomorphic to a surface bounded by a curve is a domain of finite type in a vertical plane if there are two conditions. The restriction of the projection to the domain has to be proper, and there are finitely many topological critical points. So here we have an example of such a thing. So if you consider domains of finite type and you apply the Poincaré-Reeb construction, you get a nice planar graph with finitely many vertices. Genericity, again, if we don't have bitangency. And this here is an example of domains which are not of finite type, because the first condition is not satisfied. There is no properness on of the projection. And what I want to consider next is I want to show you that the Poincaré-Reeb graphs turn out to be complete invariants of these domains of finite type with respect to the vertical equivalence. But what is the vertical equivalence? So just we want to capture the combinatorics of the domains we are considering, and for that we will care about preserving the horizontal order of the critical points. So this can be encoded in this technical definition, but the idea is that we care about preserving the horizontal order of the critical points. So for this equivalence, it turns out that the Poincaré-Reeb graphs are complete invariants. So two domains of finite type are vertically equivalent, if and only if their Poincaré-Reeb graphs are vertically equivalent. So this is a nice feature of the Poincaré-Reeb graphs that holds in such generality. And maybe you think maybe there are some other objects that could be complete invariants, so why use the Poincaré-Reeb graph? But it's not so simple to find complete invariants for the vertical equivalence. For instance, if you think of in terms of what I was talking before with comparing two total order relations, you might want to consider two domains that are generic. You numerotate their, these, first of all, these are not equivalent because their graphs are not equivalent. But if you try to find some other objects, like permutations that could compare the two, you might associate, for instance, two total orderings on such a graph, the red one on the curve and the green one on the vertical foliation, and the same for the second one. If you compare the two total order relations for each of the domains, you will end up with a permutation. And in this case, you see it is the same permutation. So they are not equivalent, but the permutation stays the same. This is not a complete invariant. Permutations didn't work so much. And what is also interesting in the case of domains of finite type is that the graphs capture the Euler characteristic. I mean, they preserve the Euler characteristic of the domain, so it might be a useful tool. By the way, I didn't say that maybe I see as a possibility of apply in the future. There might be useful to apply Poincaré-Reeb graphs for non-convex optimization, and the polar curves might turn out to help. So I think it's worth mentioning now that I was. So you see that by this proposition that preserve the fact that the Euler characteristic is invariant actually recovers. Oh, sorry, this doesn't. Recovers the result of the fact that for disks, the graphs are trees. But it's not complicated to see, maybe. Okay, and now just in the last few minutes, maybe, I will tell you the third part, which is a realization for the case of algebraic domains. So the extension of the previous result for a more general setting. However, in these more general settings for algebraic domains, we don't have an effective realization. We prove the existence of such graphs. So the idea is that given a graph that is a transversal graph. Sorry? Existence of a domain. Yes, thank you. So given a graph that is transversal and generic, so no two vertices on the same line and so on, as I was saying before, can we realize it via an algebraic domain? And yes, I mean the first, the main part of this generalization is for compact and connected graphs. Yes, they can be realized. This is this theorem in the preprint with Baudin and Popescu-Pampu. And how do we prove this? The proof consists in 3 steps. We first realize this, so we start with a graph. We realize it with the domain that is bounded by a smooth function, by the level set of a smooth function first. With some, first maybe I skip for now the details, but just first step. Then use an approximation type, Weierstrass type approximation theorem to approximate a smooth map via a polynomial, and in this way you could get a curve in a small neighborhood of the previous level of the smooth function. But this would not be enough, because we are interested with these graphs in the critical points and the order between them. And when we use this approximation, or even with the smooth function, we might end up having some, actually no, here at the approximation step, we might end up having some more vertical tangency points. So we need to control those. And that's why it needs to be an adapted version of Weierstrass, where we control the points of vertical tangency with some partial derivatives with respect to y. And then this is in a nutshell, because there are technicalities behind. And maybe just a slight, maybe short thing. It's that maybe you ask, okay, in the beginning I showed you also non-compact, maybe even non-connected algebraic domains. What about those? Could those also be realized, especially now that we have this compact realization? And for that, we also had, we thought it's useful to have a general definition of the domains that one could consider. So for considering more general cases, we just take a lower constraint, a less strict constraint, where we just impose that the restriction of that projection with respect to the curve is proper. So no longer with respect to the blue domain here. And then for these domains, you see now we don't have any more finite graphs because these are unbounded. So we needed to enrich the Poincaré-Reeb graphs definition. In the case where the boundary is a line, homeomorphic to a line, we can have these three situations. And there are arrows that encode the fact that the domain escapes towards infinity, and there are some feathers that show that there are some infinite vertical segments in the domain that get contracted. So these are new Poincaré-Reeb graphs for the non-compact case. And when this is the simplest case where the boundary is just a line, homeomorphic to a line. No, doesn't work. For this situation, in the case where you are given a graph that is connected, that is non-compact, transversal, we also, by using the first result, we could extend the realization theorem. But maybe the next picture can show you. So the idea is that we want to add branches, and this is quite a classical idea in real geometry, that you, in order to add branches, so this is the key idea. We cut this, if we have, for instance, an ellipse, we just cut it with a line, and then, or with a precisely, like, well-chosen shape you want. And you take, of course, if that is also, chosen to be algebraic, then take a nearby level. The nearby level will have, here in blue, branches. So in this way, if, for instance, you want to realize this graph in the left bottom corner, just consider it as a compact one by replacing the arrow with the dot, and add a parabola to the previously constructed curve, and take a nearby level, you will end up having such a graph. So that, maybe that's just briefly the rough idea. For each of the cases from before, if you choose if you pick a well-chosen curve, you can construct your, And then one more thing, I want to say that these graphs turn out to be useful also for computing the number of ovals and of lines of the boundary of your domains. And moreover, you can also control the complement of the given domain, because it turns out that if you take the graph of the complement of the domain, the two are determined one by the other. So the interior graph determines the exterior graph. It might be interesting to see how they are, how they meet. Okay. With this, I would like to thank you for your attention.